Hi, I'm Anthony Folk,
My name is Shaw Liu.
and we're going to talk about the application of the design axioms for forging preform design. In particular, we're going to be talking about this part you see up here. It's the nose landing gear for the 777 plane. In the middle in the yellow there is kind of a CAD representation of the final product, and we're going to talk about the design of the forging to make this thing. So just a quick couple of definitions to get you familiar with our terminology. The die is just the tooling system consisting of the mold to form the workpiece. When we talk about finish, we typically talk about the die impression that yields the final forging geometry. In this particular case, it's kind of defined. It's a legacy forging, so that's a constraint. So there's kind of an overlay of the forging. It's in transparent. I don't know if you can really pick it up over the final part. Just to give you a sense of scale, that thing is 65 inches long. It's about 60 inches wide, and while the final part is hollow and weighs about 550 pounds, the forging itself weighs closer to 3,000 pounds. It's made of 4340 steel. So we're primarily focused on the design of the preform, which is a gentle impression that provides the forming for the finished geometry. And that kind of shows the forming of the preform, and that's an overshot of the preform in the finished die impression. So the objective here is kind of to design a design process. We want to design an efficient preform design process. Typically, when we go in this, it's kind of a haphazard methodology, relying heavily on experience and how we've always done things. So we wanted to understand a lot of the coupling and a lot of the design aspects. In particular, while we're focusing on this forging, we make other nose landing gear forgings, part of this forging family, and they're very similar. So a new design would be kind of taking a tweak on an old design and adjusting a few certain things and calling it the new design. So that's kind of a flow chart. We get a product request, which is a fixed, supplied forging. We'll do some rough analysis using CAD. We'll do some finite element analysis and simulation, and a lot of it's kind of up to the designer, engineer's experience and discretion. And once that iterative process is complete, we'll go on to generate a drawing. So to talk about the decomposition is Shaw.
Okay. Top level decomposition. Or FR0 is to provide the efficient preform design process. The corresponding DP0 is the preform forging design manual. To go through the complete preform design, we need to come up with a shape first, verify that the shape is what we want, then provide the tooling drawings to convey our design intent to our suppliers. So CME-min breakdown of our FR0 would be to establish the preform shape first. The DP for it is a three-dimensional CAD drawing model of the preform. Next one is verify the quality of the preform, and that's done through FEM simulation. And lastly, to generate the preform tooling drawing. So we want to expand further on the design process for establishing the preform shape. First of all, to ensure a balanced material distribution for the preform to finish, we must first assess the finished forging volume allocation. We do this by slicing up the finished forging with a VBA script embedded with our CAD software, and then export the data to Excel, and where it's plotted volume versus distance. And this gives us a visual representation of the volume distribution in the finished forging. And we use that as a baseline to conceptualize our preform shape. Forging parameters and plan view areas are also looked at to estimate how much extra volume is needed in the preform to ensure a balanced flash pattern and adequate closure. So based on the finished forging assessment, we conceptualized the preform shape in the form of a CAD model. That's the finished forging, and that's the conceptualized preform model. then the shape is scaled up by the thermal expansion coefficient at extrusion temperature and converted into a surface mesh prepared for FEM simulation. The simulation result provides with a feedback, and we might have to go back and tweak the preform shape. So this is a iterative process. While we're tweaking the shape of the preform, we have to consider the manufacturability of the shape, and that leads to material deformation and die design. Here is the animation of the actual extrusion process. The top die comes down, it locks with the bottom die, and it contacts the piece and extrudes the incoming stock through the impression. One of our primary concern, which is listed as FR1332, is the consideration of die life. We've experienced cracking and failure in other similar jobs in the past, so we expected to see some high stress areas near the neck of the extrusion. Stress simulation was done on the system for the extrusion process, keeping track of the load and the volumetrics, and that confirmed our suspicion. So the solution to this problem is to introduce the segmented die system, splitting the critical areas so the stress risers gets eaten up by the interface tolerance. Coincidentally, where we split the die block just happens to be short of the maximum depth that the outside machine house is able to machine the impression. So in other words, that we have a coupling situation here with one DP satisfying two FRs. Going further down the list, we also have to consider the environment that the die system operates in. Looking at the press dimensions, truck operation space, piece ejection, and so on. So this is a model of our die system sitting in the 18,000-ton press. And here is where some of the physical integration of our design comes into play. The press only has a daylight of 127 inches. So that limits how tall the dies can be and how much the top die can move up, and also how much room we have to get the piece out of the die. Here, a shelf in the impression is introduced to help the incoming stock locate within the die. It also helps to stabilize the workpiece at initial contact. Picturing the incoming stock is a square sitting on a triangle. The one you see on the right are shoulder blocks. Those are used to prevent lateral bulging at the initial stage of extrusion, which was predicted by the simulation. So they are the only portion in contact when we go die to die. So the top face of the shoulders needs to be sized large enough to withstand the entire forging tonnage. Here is the ejection system designed to push the piece out of the die. So let me back up a little bit. Notice, you're probably wondering, notice on the upper right diagram that you notice the top die is somehow larger than the bottom one. Because we want to, at the beginning of the design, we want to fix our die cost at a certain figure, so that becomes our constraint. So the highest stress occurs in the upper segment of the bottom die, so that was sized to be thicker to withstand the pressure, and the lower segment experienced minimal stress, so it was just sized just large enough to support the rest of the system. Keep in mind that this entire die system weighs about 30 tons, so it's very unlikely to tip over without some serious lateral forces. So with that, I'll pass back to Anthony.
I know we're running a little late, but give me 2 minutes to finish through this. So as I talked about earlier, our kind of historical process is shown up there on the left for a typical nose landing gear forging. And I threw these pictures in primarily because Professor Brown mentioned he liked hot metal forging pictures. So it's kind of an open die process. We work the material with stock tools. We squish it down and we cut them in half. But that process, while we may save some time on manufacturing, we can manufacture two at once. We get a lot of variability in that split weight. So the volume going into this preformed die and eventually the finished die varies by as much as 20% of the weight, whereas historically we're about 6% of the weight. So this is kind of our conceptualized new process where we want to just take the functional requirements of the design. We want to maximize the material input, minimize defects. So that's all kind of and verify the quality of the preform, our second functional requirement, to try to determine if this thing is any good. So it's kind of another overview of the preform and the finished die, and then the end result where we get a much more uniform flash pattern. Probably another definition: flash is all excess material that gets thrown away after the forging. So then we apply a tool to determine the rate of fill, and kind of look at little vectors for each element to decide which way they're going, if there's any propensity to cause any defects. So the functional requirement would be to provide a defect-free forging, and then this is showing the design parameter 2.2.1 of the rate of fill. So there's kind of a summary of our current processing efficiencies with that split process. It's a high scrap process. It's a high rework process, and subjectively approaching this design is some of the advantages that we can have. Thank you for your attention.
Okay. Questions? I got one comment while you're thinking. You're allowed to take the information that you get tonight and integrate that into your write-up. Actually, I encourage you to do that. And some things, but you don't have to necessarily rework everything. You can put some comments in. Some of the FRs and DPs here might be stated a little bit better. Let's go back to there. Go. So we need defect-free forging. So by somehow controlling the rate of fill, we're getting that, right? Well, one of the things to watch out for is if you're sort of jumping over, if you're jumping over domains. And one of the things that I've discovered working with the class this term is that there's a tendency sometimes to move over a domain as you move down. So the rate of fill, this is a DP, but so there's something that's controlling the rate of fill. You're trying to get the defect-free forging. So there's it may be that this would be a better process variable, controlling the rate of fill somehow. And then anyway, so it's something to look at, or maybe this could be reworded a little bit. But guarantee full defect-free. Maybe it's good. Anyway, so that maybe doesn't apply here. But take a look for where you start moving over domains. We saw that in the last one where we were actually, there was no. It was anticipating the result a couple things ago. Anyway, very good. A lot of decomposition and a lot of FR. How many FRDP pairs do you have?
The big matrix.
Yeah, well, that's fascinating. And the landing gear work is always interesting. Yeah, are you guys doing the 787?
Not currently yet, absolutely. But this is a legacy forging that we were just awarded. We haven't made it before.
Oh, you haven't made it before? Because the 777's been around for a while.
Right.
Yeah.
Competitor was making it.
Oh. Does Wyman Gordon make the 747?
We make a lot of parts for it, yeah.
Yeah. The landing gear for the 747?
Yeah.
Yeah, right. That's what I thought. I've seen that before. All right. Any questions? Comments? This was interesting because it was designing the design process for this. So thank you very much.